Hey everyone, my name is Devon, and today me and Aditya from the Mekmahan group will be presenting an overview on our project, Advancing Environmental Mapping at Crop Health Assessment with Drone Imaging. The USDA currently monitors crop health mainly through manual field surveys, which are costly, time-consuming, and limited in coverage. Most existing studies only address isolated aspects of crop monitoring rather than providing a comprehensive approach. Our research is designed to address these shortcomings and create a more integrated solution. Our solution is to develop an autonomous drone capable of capturing high-resolution images of crop fields. These drones will fly over agricultural areas, collect photography, and then process the data using convolutional neural networks on the ground. The processed information can then be shared with agencies such as the USDA to support more efficient and wide-scale crop health monitoring. This work is important because it directly addresses the USDA's limitation. Could you go to the third? Yeah. This work is important because it directly addresses the USDA's limitation with costly and narrow ground surveys. By using the drone, we can cover much larger areas with high-resolution imagery, enabling earlier detection of crop health issues. This early detection not only helps us stabilize the food supply, but also allows for timely interventions that reduce crop loss. Our system integrates the data collection, processing, and delivery, providing a complete and efficient solution for modern crop monitoring. For our project, we'll use the Holybro X500 drone frame, which is lightweight, durable, and can carry many components like a Raspberry Pi, GPS, and flight controller. The drone will have 4 motors with propellers, each controlled by an electronic speed controller. A Pixhawk 6C will handle flight control, power, and GPS. The Raspberry Pi will act as a camera trigger, while a Phoenix 2 FPV camera will capture aerial image mounted directly on the frame. To operate the drone, we'll use a Zorro radio controller along with the Radiomaster R81 receiver. This setup gives us an efficient, customizable platform for aerial crop monitoring.
We're going to be using 2 websites for creating our datasets, Kaggle and Mendeley. There are way too many datasets affecting crops, so we could not find a significant number of images per disease to have the model detect specific conditions. Thus, we made sure to only classify healthy and diseased crops. We plan on training a CNN with around 87,000 images, use crop labels and health labels, while applying transformations to each image to reduce any bias. So here's some background into CNNs. The convolution layers extract features from input data by moving small matrices called filters across the image. At each position, they multiply the filter values with the corresponding input values and add them up, generating a new set of values called a feature map. This is demonstrated through the image in the top right. Pooling layers reduce dimensions by lowering the resolution of the outputs of the convolution layers. This helps in reducing the computing power needed for the overall process. The flattening layer concatenates the n by n dimension array outputted by the convolution layer into a 1D array. The flattened layer outputs are then fed into the fully connected layer, so that they can undergo linear and nonlinear transformations using weights to get probabilities for the classification of each input. Each probability corresponds to a class. The class with the highest probability is where the CNN would classify the input image. GradCam is a method used to find out where the model is focusing through the heat maps. So first is some vocab. Gradients tell how much of the model's predictions are altered per unit change to a pixel on the feature map, and feature maps are outputted by every convolution layer in the CNN, and only contain certain features from the original image. So in the first step of GradCam, the gradient of each pixel is found. Then they are averaged out so that a single value representing the entire feature maps to represent the entire feature map's importance to the overall classification. That's called a weight. When all the feature maps are multiplied by their corresponding weight, they increase or decrease their corresponding features' red or blue accentuation. Finally, the feature maps are summed and overlaid onto the original image, creating a heat map that can show the model's focus. You can look at the image of an example diagram to the right. So we do not have any results yet because we're not done with our first prototype, but we're very close. So compared to other research being done, our methodology is more cost-effective, quicker, safe, and with more replicable results. In the future, we wish our prototypes, our drones to be autonomous, contain live analysis abilities, and have our ML model respond to each image taken. Once we have a suitable product, we plan to use our work on commercial farms or large environments such as forests. So we're currently working on the integration side of our hardware, meaning that we have to solder our Raspberry Pi and other parts. Then we can import the code so that we can start our initial test flights and send video feed to the computers. On the software side, we're using Google Colab because it allows for easy collaboration. We recently fixed an error with the paths of the images and how the code reads through them. We have a lot of code done, and we're finishing up the model code, but still requires extensive training and debugging, as it might not be very accurate when it's tested in the field.
We would like to acknowledge ASDRP for giving us all these resources and our advisor, Dr. McMahon. And we would also like to acknowledge our lab alumni and current members on our group. Thank you.